You and your friend are traveling from Los Angeles to San Francisco, but you can't leave at the same time. You're going to leave at 8 a.m. Your friend can't leave until 9 a.m. But your friend travels a little bit faster than you. And so the question is, who's going to get to San Francisco first? So to set up this problem, let's draw positions, times, velocities, and then we can start to solve. Okay, so first, let's establish positions. Here is your car. We'll label it A. Okay, and you leave San Francisco. We'll give it an initial position of X, A, initial, and you leave it at an initial time, T, A, initial. You travel with a constant speed, VA, so there's no initial or final because it's constant throughout the whole motion, and you get to San Francisco, which is at a different position, your final position, at some final time. Okay. Now, your friend, just label it B, has their initial position. It's the same value, but it is describing a different system. So we're going to give it its own coordinate system, XBI, starting at a later time. So this is one reason to be careful with the variables. The initial time for B is different than A. Traveling a little bit faster, VB, and getting to the same position, okay, but at a later time. Okay. So we have the positions defined on our diagram, on our picture. We have the times defined, and we have the velocities defined. We know there's no acceleration traveling at constant speed or an average speed the whole time. So one question is, well, what do we know here? So we can make a list of knowns over here and ask, what do we know? Well, first of all, if we establish a coordinate system, we can always choose a position to be 0. And here, since they're both starting in Los Angeles, we can choose Los Angeles to be x equals 0, which I show with my coordinate drawing there. Okay, so we know that XA initial equals XB initial equals 0. Okay. We can do the same thing with our time. We could say we start this earlier time. I apologize. So that we're not going to do the same thing. We could choose a 0, but we're actually told you left at 8 a.m. So we're going to go ahead and do that. 8 T A initial equals 8 o'clock a.m. All right, and TB initial equals 9 o'clock a.m. All right. You travel 50 miles an hour. Okay. And your friend travels at 60 miles per hour. You both get to San Francisco, so you both have the same final position, and that's 400, apologize here, 400 miles away, since we chose Los Angeles to be 0. We don't know these final times. We're trying to figure out what it is. Which one is an earlier time? Okay, so that's what we know. So let's go ahead and write. We're trying to find T A final and TB final. That's our question. What are those two values? So this is all of our pictorial representation, everything we need to be able to now use our equations correctly and effectively. If we skip some of this, then when we start actually plugging in numbers, we can make mistakes very easily. And this is especially important when we get to more complex problems. There is a tendency to want to jump away from all this and just start plugging in numbers. But we're focusing on this process because that is what's transferable to more complex problems and even additional courses in other fields of study. So this was critically important that we took the time to be very careful to define variables and to list what we know. So now we can start solving. Let's go and start for A. I'll draw a line here and see what this algebra gets. Okay, so A, I'm trying to find the final time. No, it's traveling at constant speed. Okay, so we can use a relationship. We have an initial time, and we can just use our relationship that relates position and time, which could be x b final equals x b initial plus velocity. Oops, sorry, I'm doing I apologize for that. Times the time period, which would be t a final minus t a initial. Okay, now our coordinate system says this is 0, so I can mark that out. And our time here, the A, that's 8 o'clock. So we're trying to find this. So we need to leave, we know this value, 400. We know that, that's 50. And we know that, it's 8 o'clock, so we're trying to find this. So solving for that, we get TA final is going to be equal to XA final over VA plus TA initial. And we'd get the same equation for B, plugging in the correct value. So for A, we have 400 miles, okay, and going at 50 miles per hour, and then we're going to add 8 o'clock, which is an hour. Okay, so this is in the correct units. The miles cancel, the hours in the denominator of the denominator, meaning it flips to the top. Okay, so 400 divided by 50 is 8, and so the answer here is going to be 8 hours plus 8 o'clock is going to give us 1600 hours, or it's going to give us 4 o'clock in the afternoon, 4 p.m. Now, in the same way, we could plug in the values for B, since we know the same variables. We know that position is the same, the distance traveled is the same, the velocity is 60, and the initial time is 9, and so 400 divided by 60 is 6 2/3 hours, plus 9 gets your friend there actually a little bit earlier, 20 minutes early before you. So that is an example. Here's the math that we used, but we were able to do it carefully using all of our defined variables.